Alright, so this video shouldn't be very long. We're just talking about universal gravitation and planetary motion. So pretty much what we're talking about is how gravity affects things that are either very large or very distant from each other. So rather than talking about how things affect each other on the surface of a planet and calculating the force of gravity of something near the surface of a planet, we can talk about how the sun has a force of gravity on the Earth and how that affects the Earth's motion. And as we are talking about everything throughout your entire coursework at Sci-Fair, make sure that if you ever have a 0, whether you think it's an important grade or not, make sure you turn it in because zeros drastically decrease your grade, like Aladdin in that one scene of the Disney movie. Alright, let's get going. Veritasium has a very good video on weightlessness and gravity on astronauts. So I recommend you check it out. You can find it on my slides. The link is in the slides if you download the slides, or you can search Veritasium, why are astronauts weightless? Because gravity is still holding them in orbit around the Earth. So there is gravity out by the astronauts. So why are they floating around? And he helps answer that question. So there's a lot of stuff on this slide. Let's take a look at what all is on this slide. First, we've got the equation for the force of gravity between any two objects. This can be between you and the person sitting next to you in class. This can be between the Earth and the Sun, between the Earth and the Moon. It could even be between Jupiter and the Earth, or any other two objects in the entire universe. This G here, capital G, is not the same as the acceleration caused by gravity. The acceleration caused by gravity only works near the surface of a planet. This capital G is the universal gravitational constant, and it works for the entire universe, no matter where you are in the universe. It has, it is 6.67 times 10 to the negative 11. That's the magnitude of that number. And it has a unit of newtons times meter squared divided by kilograms squared. You don't need to worry about that unit though. Don't freak out about the unit. In most cases, if you're in high school, we will never ask you to derive that unit, and then you have to remember that unit or else you get points taken off. No, that's not what that unit is there for. It's not to trip you up. Just make sure that we have newtons as our force of measurement, okay? Or for our unit of force. It is 10 times 10 to the negative 11, which means it is a really insubstantial number. And that makes gravity a very, very weak force. It is the weakest force of all the forces that we know in the universe. It also means that the masses up here have to be very, very big in order for the force of gravity to be significant. M1 is the mass of the first object, M2 is the mass of the second object, and remember our standard unit for masses are kilograms. And then r is the distance between the centers of the masses. Okay. That means we can use this equation to find the force of gravity acting on us on the surface of the Earth. We just have to remember that the distance between us, if this is the Earth and we are standing on the surface of the Earth, that is a really big giant, then our distance between our center and the Earth's center is roughly the radius of the Earth. And you should be able to calculate the force of gravity. If you do this calculation, the force of gravity would be the same as the mass times the acceleration caused by gravity. Should be. There's also some other really good physics videos by a channel called Minute Physics. One is called What is Gravity, and the other is called What If the Earth Were Hollow. Those are both very good videos, and I recommend taking a look at those after you take a look at this video. So on this page, we have some examples of relative forces between two different celestial objects with varying masses. So over here in the top left corner, we have what looks to be the Earth with a mass of m2 and the Moon with a mass of m1. And they are a distance d apart. Now the force between them, we're just going to call that a generic F. On this picture, we're not really looking at specific amounts of force. We're just comparing the forces between two objects if we change them. The next picture down from that top left picture is if we doubled the mass of that moon with a mass of m1, whatever m1 is. And notice, if we have, let's write the equation that we have on this slide. Force of gravity is g m1 m2 divided by r squared. So if we double m1, we wind up doubling the force as well, because they're multiplied together. If we don't double m1, but we double m2, the force is still going to be doubled. It doesn't matter which object's mass we double. And then if we double both of the masses, the force between them is going to be 4 times greater, because over in our equation, we're multiplying those masses together. So 2 times 2 is 4 in comparison to the original force that we had. But what if we start changing the distances? What if we double the distance? If we double the distance, our force is going to be 1/4 as big. The force between those two objects gets smaller. That's because for distance, it's at the bottom of a fraction. So the bigger the denominator of a fraction is, the smaller the number itself is. So if you have 1/2 of something, or 1/5 of something, 1/5 is smaller than 1/2. And the reason it's the force between these two objects is 1/4 of F is because we have to square the distance. So 2 squared is 4, which winds up being 1/4. Then, if we bring the two objects closer together, we get a larger force, 1/4 of the force. Sorry, no, 4 times as much force. And remember, my middle school math teacher always said, if we're dividing fractions, don't ask why, invert the second and multiply. So this would wind up being 1 times 4/1, which is the same as 4. So we get 4 times as much force. So if we have a student with a mass of 80 kilograms and a student with a mass of 40 kilograms, student A and they are standing 20 meters apart on a dance floor, and they feel the attraction of gravity, how much force are they feeling? And the link here is a link to the chicken joke from The Big Bang Theory. It's a little bit, the jokes in the Big Bang Theory are a little bit above the heads of high school physics students, but if you take it to college physics, you start to realize that these nerdy jokes are actually a little bit funny, if not very funny. But let's take a look at this problem itself. So what are we given, right? We're going to use the guess method. So we're going to find our givens, unknowns, the equation, substitute, and solve. So our given, we have a mass of 80 kilograms, a second mass of 40 kilograms, and a distance between them of 20 meters. So we are looking for the force of gravity between the two of them. And the equation is the equation we had before. So if we substitute, G is 6.67 times 10 to the negative 11. M1 is 40. I'm sorry, M1 is 80. M2 is 40. But it doesn't really matter which you put where, right? In math, we have the property, if we have A times B, that's the same as saying B times A. If you want to put it in terms of numbers, if we have 3 times 2, we get 6. And if we have 2 times 3, we also get 6. And then the distance between them is 20, but don't forget to square it. Plug that into your calculator just like that. And the solution is 5.3 times 10 to the negative 10. So it is still a really, really small amount of force. In comparison, think of a gram. A gram is about the size of a grain of rice, or about the size of a stud earring, a small stud earring. So the force of gravity on a gram should be 0.0098 newtons, or if we want to put it in scientific notation so that we can compare it to our answer, then it would be 9.8 times 10 to the negative 2. That's significantly bigger than the answer that we got for the force of gravity between the two students. So this is a very, very small, very unnoticeable force. So now let's talk about the planets. The person that we like to talk about with planets, especially in high school physics, is not Copernicus, although Copernicus was very awesome to realize that we were not the center of the solar system. But the person we're talking about is Kepler. And he was alive at about the same time as Galileo, and Isaac Newton. So that means he discovered all these things just by crunching numbers and looking at the raw data that some other astronomers found at the time. And remember, this is back before the times of smartphones and calculators, and to some extent, even telescopes were a new thing. So the amount of just pure calculation that this guy did to come up with these laws is astounding. And it makes me wonder what we could do today without YouTube and Twitter. Although they can be very powerful tools. After all, you're watching this video on YouTube. So the first law is the law of orbits. All planets move in elliptical orbits, which is essentially like an oval, with the sun at one focus. So over here on the right side of the screen, there's 3 different ellipses. And you notice as they get stretched out, that bottom one is very stretched out, the focuses between those two, the focuses have a larger distance for the one at the bottom than they do the one at the top. The one at the top is also called a circle. A circle happens when the focuses of an ellipse are at the same point. So all planets move in elliptical orbits rather than perfectly circular ones. And the sun is at one of those ellipses. Or sorry, the sun is at one of those focuses. This is also true of any other object in our solar system. So this also counts for moons or planets. Moons tend to be a little bit more circular in orbit than planets. This also counts for comets circling the sun. Comets tend to have very, they tend to be more elongated ovals. There's a special word for it. It starts with an E, and I can't remember it. It's another word for weird, but I can't remember it. Well. You won't be tested on that, at least not in my class, so don't worry. Planets and moons tend to be more circular. And you may want to know at least what a semi-major axis is and a semi-minor axis. Those might come up. So if we go from the very center of our ellipse, the semi-minor axis is from the center to the closest side, and the semi-major axis is from the center to the farthest side. And notice it goes through one of the focuses. The second law is the law of areas. And this slide does have an animated GIF, but the recording system I'm using doesn't want to animate anything for me. So take a look at some animated GIFs of Kepler's second law if you get a chance. The law of areas says that for every equal amount of time around, say, the sun, the area is going to be the same. So if you look at the picture that's on the right of the screen, you can see a lot of little blue dots. All those little blue dots are equally spaced in time. Planets do not move at the constant speed all the way around the sun. They go slower when they're away from the sun, and they go faster when they are closer to the sun. So when they are further away from the sun, the amount of distance it takes, the amount of distance they travel is not the same as when they're closer to the sun. But the areas shaded will be the same. And that's kind of neat. And he had to figure that out just by crunching numbers without calculators, without smartphones, without Microsoft Excel, anything like that. It was kind of amazing. Kepler's third law is the one that gets us all of the is the one that we can use for calculations, at least some easy calculations. It's called the law of periods. And what it says is that the period of two, we'll call them planets for now, the period of any two planets, and remember capital T is for period, those periods squared are equal to the distance between those planets and their star cubed. So in that top equation, we have a couple of different things going on. The A's and B's are just a label for whatever planets we're using, right? So it could be Mars and the Earth orbiting the sun. It also could be any to the moon and the International Space Station, like moon and space station orbiting the Earth, or it could be Europa and Io orbiting Jupiter. Europa and Io are moons of Jupiter. So the A's and the B's are just labels to what objects we're talking about, but you do have to square the periods and cube the radiuses. Now Newton's version of Kepler's law is the one at the bottom. It takes a little bit of math to get from Newton's universal law of gravitation and Kepler's law of periods to this equation. So we're gonna not worry about that for now. There are plenty of YouTube videos that can show you how we get from this equation and this equation into that one on the bottom. The only thing we need to worry about here is this capital M. So for the capital M, that is the mass of our larger object. So if we have information about a moon and the period of the moon going around a planet, this is actually the mass of the planet. Or if we have the period of a planet going around a star and the distance of the planet around the star, capital M is the mass of that large star. It's not the mass of the planet. Capital G is still the universal gravitational constant. And just in case it comes up, meters and kilometers are too small of a distance for space. So instead we use astronomical units, which is the average distance from the Earth to the sun. Remember, the Earth is not going a perfect circle around the sun, so it does have to be the average. But scientists have come up with a consensus of what that average is, and that is what we call an astronomical unit. If you need it, and on my homework in my class, it's usually given, but it's also something that's very easy to Google. You can look it up using a Google search really fast. So let's take a look at this example. We have a moon. This is a moon of a different planet, a distant planet not in our solar system, and it has an orbital radius of 0.57 times 10 to the 8 meters and an orbital period of about 26 hours. Use this information and Newton's version of Kepler's third law to find the mass of the distant planet. So first thing I notice about this, we have our givens. We have two very important givens, 26 hours and an orbital radius. Right? So we have the radius. And it's given to us in meters, which is good because we always want things in meters, seconds, and kilograms, especially. But we are given a period of 26 hours. That one's no good. We need to change that into seconds. So make sure you do a unit conversion. 1 hour is 60 minutes. 1 minute is 60 seconds. So this should be 26 times 60 times 60. So lots of seconds to estimate. 93,600 seconds. That's the period that we want to use. So now we have to plug everything in. We have our givens, and we know that we're solving for the mass. So now we need substitute. So period squared 600, that will be squared, equals 4 pi squared. R is 2.57 times 10 to the 8th. We're going to cube that, divided by 6.7 times 10 to the negative 11, and we're looking for the mass. So leave that alone. I always strongly recommend just plugging it into the equation as is. Always write your equation first without any plugins, without any numbers added into it, and then very next step, write your givens into that equation exactly as written. Don't try to solve anything in your head just yet. I've seen so many errors of students trying to skip a couple steps. Don't do that. Make sure you get it right the first time. So I have a nice TI calculator, so I will be doing a couple of these steps, like all this on the right side of our equation. I will be doing that all at once on my TI calculator. Okay? But to start off with, 93,600 squared should be a really big number. I am going to abbreviate that because it is really big. Times 10 to the 9. So we have 4 pi squared times 2.57 times 10 to the 8 cubed divided by 6.7 times 10 to the negative 11. So on the other side, we have 1 times 10 to the 37 over mass. So we have to multiply by the mass on both sides. Multiply the mass on both sides, and then divide by 8.76 times 10 to the 9. So the mass of this distant planet should be 1.15 times 10 to the 27 kilograms. Oh. Also, check out some of these other videos.